Lorenzo, and thanks for inviting me. Let me share the screen first. Can you see the slides?
Yes, absolutely. Thanks.
So, yeah, first of all, I'll start from a short introduction.
You were prepared. You had the slide. Great.
Well, I had it.
Fantastic. Yeah, thanks.
So basically, as Lorenzo said, I'm a PhD student, the last year PhD student at the Technical University of Munich, and my PhD is sponsored by Siemens. And so basically, I'm supervised by Professor Slobodan Ilic, and he's also working at Siemens. The main topics of my PhD are, so my entire PhD is based on the idea of 3D pose estimation, and it lies around this idea from synthetic data. The thing is that at Siemens, there is a lot of industrial parts, and there's a lot of 3D models for them, and we want to basically estimate their pose and detect them and classify them. And the problem is that we don't want to acquire the sequences of real images for all those objects, but we want to use the 3D models that are available. And for this, we try to bridge the domain gap between the synthetic and real data and train the algorithms on the synthetic data and make it work on real data. Yeah, so that's pretty much it. That means I work with domain adaptation and object classification, also detection and pose estimation, and metric learning as well. So yeah, that's a short introduction about myself. If you're interested, you can contact me at any time. Lorenzo is also going to share the LinkedIn link, but you can also write me an email or phone. It's a German phone if anyone wants. Yeah, so that was a bit about myself. Now I'm gonna continue with the topic itself. So the work, as Lorenzo mentioned, is gonna be, I did this work during my internship at Toyota Research Institute, and this is about auto-labeling of 3D objects with differentiable rendering. Yeah, so I did it last year, and this work was presented at CVPR as an oral presentation. So when I came to TRI, there was a task that I had to solve and was pretty simply defined. And the task was as follows. We are given a single image of a street view with the cars, and we are also given the 2D bounding boxes of cars. And the question is, can we actually estimate the geometry of the detected cars? So the cars that are in bounding boxes from just RGB values. And also, can we estimate their 9D pose? 9D pose meaning the rotation, translation, and scale of the car. So 3 degrees of freedom for rotation and 3 for translation, and also the dimensions of the bounding box. And if we can do so, if we can estimate the 9D pose, we can basically, and we also know the shape, we can map the objects onto the image and project them onto the image and get the then 9D cuboids. And this allows us to recover the entire label. Why is this important? Is, yeah, because all the algorithms, all the vision algorithms are trained on such data on the labeled 3D or 9D bounding boxes. So why is it, once again, important? So first of all, currently there are no tools that do this labeling automatically. Usually there are tools to make it simple, but they still require human in the loop. There needs to be someone to click somewhere to say, okay, this is a good label, this is not, but there is no fully automatic pipeline. And we wanted to try to implement something that would allow you to automatically estimate labels without any human intervention. And our pipeline consists of 3 components. So in the beginning, we didn't know what those components should be, but yeah, we knew that it should have something like, first of all, a database of shapes, and it would be cool if it's differentiable because we want to optimize over the shape and maybe interpolate between the shapes as well. And the next component would be a differentiable renderer, such that we can reason about the shape from 2D image. And the third component is the initial pose and shape estimator to allow us some sort of optimization. So we can say, okay, this car is approximately there in terms of translation and rotation, and it also looks like this approximately, and then we can maybe refine the results. So first of all, I'm going to talk about the first component, about the database of shapes. We started investigating about this thing, and there were a couple of solutions available. First solution is DeepSDF, as you can see. The other solution is the occupancy networks. But we ended up using this DeepSDF, first of all, because of the performance. From the initial experiments, it was better. And second of all, because of the SDF representation itself. So what is a SDF representation? This is exactly what you see on the image. So this is a representation of the, basically a kind of a vector field. So in 2D, you would see this kind of image. And each value means the distance, defines the distance to the closest surface. So let's say on the boundary of the object, it would be 0. Outside of the object, depending on the convention, it could be a positive sign. So it could be like +1 here, +10 here, and further away you are from the surface, the more the value is. And if it's a negative value, it's inside the object, and it's just a negative distance. Then you can flip the convention as well, but usually it's defined like this. So this kind of surface representation is used in this work, DeepSDF, as I already mentioned, and this is, I find, a very cool work. It's a very simple neural network that basically looks like this. So what you do, you feed an XYZ coordinate to it, and also the latent code. The latent code defines what kind of shape you're gonna get. And as an output, you just get one value, which is an SDF. It's either a positive or a negative distance to the closest surface. And you can fit a lot of sample points to this network. You're gonna get a lot of values, and then you can basically reconstruct the object. And the coolest thing, what it allows you to do is it allows you to remember a lot of different shapes within one network. It can basically remember, for our case, all the shapes you can see here, and you can remember much more if you want. So for our application, we encoded all the latent codes on the surface of the sphere, and yeah, you saw the image how it moves. So basically, each point represents the car shape, and this is all inside one network that is kind of lightweight as well. So the second component is the differentiable SDF renderer. Now that we have the SDF network, the DeepSDF network, we can feed XYZ coordinates plus some latent code to it, and we would get an SDF value for each of those points. So here you see the points, and the color means the location in 3D space. And here you see the output of this. So you fed all this into the DeepSDF network. And so the value means you can kind of see the car here, the car shape inside. The value is the distance to the closest surface. And the next question was, how can we actually render this representation and make a 2D image out of it? Because what we have is just an array of 1D values and also the XYZ grid. We cannot simply render it, and usually what we need for a renderer is a triangular primitive representation, something that consists of triangles. And yeah, so with the SDF, the very common way to render it is through ray marching. You kind of shoot a ray and see when you hit the SDF. But this approach is very slow, and there is a differentiable ray marching renderer, but it's kind of slow and usually done to simulate all the cool effects like the shadows and mirroring effects, but we don't really need it for this application. What we wanted to, we wanted to have something that is really fast, and as fast as we can make it. So our differentiable SDF renderer consists of two components. First is the Zero-Isosurface Projection that allows us to take all those XYZ points and map them and project them onto the surface using the SDF. I'm going to explain you how it works in the next slide, but basically we compute the normals through backpropagation. And the second step, once we have the point cloud and also we have normals, we use the Surfel-based rendering. This I'm going to show later as well. So first of all, let's start with the Zero-Isosurface Projection. What you see here is the grid of points. So the points are in the middle of the squares, and this is the SDF representation in 2D. You kind of have a circle, and inside the circle it's negative, outside the circle it's positive, and on the surface it's 0. So what we can get is, yeah, for each of the point we feed it to the network, which is f function here, and z is the latent code, and we get the SDF. So now what we can actually do with this is that, yeah, from the definition of SDF, we can, yeah, you can also find it in the papers. If we take the derivative from the coordinate on the surface of the object, derivative of the coordinate, the derivative of the SDF with respect to the coordinate on the surface, then we get the normal. So this is basically a Jacobian, and if we take a Jacobian on the surface of the object, it's going to be close to normal. If you go too far away, it's not going to be exactly the normal. It's just yeah, kind of the path where the change is the fastest, but it's not going to be a normal in this case. But if you are not too far away from the surface, then it's going to be a very good approximation of a normal. And if we have a normal, which is basically a direction to the surface, and we also know the SDF value, which is a distance to the surface, what we can do is we can simply project the points onto the surface, which can be very simply done like this. So this is basically the normal if we're close to the surface, and this is the coordinate of the point, and this is the SDF value. And yeah, you can see what happens. We take all those points and project them on the Surfel. Yeah, so basically it's a pretty simple concept, and this allows to do us cool things. So once we had done this, we projected all the points onto the surface of the object. We can now render it, and for rendering the point clouds, usually in computer graphics at least, it's a common thing to use so-called surfels or surface elements, which are kind of disks like this. And this is used when you don't have the triangular primitives. So you don't know anything about this, but you have normals. You have points and normals, and you can compute the equation of the plane, and then basically with a certain radius you can get this disk. And yeah, in the case of the cars you can do this, and if you have like a coarse point cloud like this, you're gonna have a rendering pretty much like this here. I showed it not watertight just to understand that It's actually Surfel-based rendering, and you can kind of see circles here. What's cool that we implemented also the differentiable Surfel-based rendering based on the ideas similar to SoftRAS. You can check it out in the paper, but it allows us to differentiate back to the not only the pose but also the shape of the object, and you can also potentially optimize over the color. So I'm gonna show you how it works later with the demo. And the third component is the pose and shape estimator, the initial pose estimator. We call it CSS network, or coordinate shape space network. And here's how it works. Here's how it works. We start with the full image of the scene. And as I said, we are given the bounding boxes. The bounding boxes you can get from several detectors, like Mascar CNN, for example, or YOLO, it doesn't really matter. So you get the bounding box. And in this case, we also use the point cloud. I'm gonna show you why, but essentially you can also do it without the point cloud. Once you have the bounding box, here's the bounding box, you feed it to the CSS network, and CSS network outputs you two things. First is the image, which is of the same size, with the normalized object coordinates. So each color here represents a 3D position, or basically the surface of the car. So if you take each color and visualize it as 3D coordinates, you're gonna get the shape of the car, the front of the car. And the second thing is the SDF latent code that we feed to the DeepSDF network. So once we have the code, we can feed it to the network and we get the full shape. And again, we use the coloring, which is basically the coordinate coloring. Each color represents the coordinate. And if the object is normalized, it's going to be a normalized object coordinate. And with the NOx, what we do with the NOx prediction, since we have the point cloud, we can back project it onto this point cloud, and we would get this here, a point cloud. This is the ground truth point cloud with the back projected normalized coordinates on it. And since we have the object shape and we also have the ground truth point cloud with the projected normalized coordinates, we can estimate correspondences between them. And given the correspondences, 3D correspondences, we can apply either the Kapsch algorithm or Procrustes algorithm together with the Ransack to eliminate outliers. And with this, we're gonna get a full 9D pose. So with the Procrustes algorithm, you get the rotation, translation, and scale just from knowing the correspondences between two 3D objects. And like this, we get the initial estimate of both the 9D pose and the shape of the car, thanks to the SDF vector. And now I'm gonna show you basically how this components come into play. This is where the optimization part starts. We take the estimation of the SDF vector, feed it to the DeepSDF network, and get the shape of the object. Next, since we know the initial estimate of the 9D pose, we transform the object, we apply the rotation, translation, and scale transformations. And now we do two things. First, we feed it to the differentiable SDF renderer to get an image of it. And since we already have the output of the network, we can optimize it towards this output of the network. And yeah, you'll see how it works. And the other thing, in case we have a point cloud, we can also optimize it in 3D by comparing the distances between the transformed shape and the ground truth shape. And what we then get, if we do the two optimizations together, we get a nice alignment both in shape and the pose. The next thing, what you can also do if you have this pipeline, you can actually do this optimization on real images. And then you can do an auto-label verification. This can be like a simple verification, like a bounding box comparison and things like this. And using this simple procedure, you can also check our repository later for the code. Using this procedure, you can fill the labels to the label pool and use this estimation from the real data set to tune the network or retrain the network to get better and better pools, the NOx estimates than before. And if you have better NOx estimates, you're gonna get a better pose and shape, essentially. So now I'm gonna show you an optimization example on a kitty frame. So you see 3 cars and we optimize them in both 2D and 3D. And it looks pretty much like this, especially I find interesting the third car because it changes the shape a lot to fit both the points and the image. Yeah, so now I'm gonna show just a couple of quantitative results. So basically what we did to evaluate this is we took the state-of-the-art algorithms in lidar and binocular detection and pose estimation. And we trained those algorithms with original ground truth labels and with auto labels estimated by our pipeline. And what we found is that the performance is actually very good, especially when you talk about the less strict metrics with the intersectional union of 0.5. And you can get really, really good estimates here, basically saying that you can pretty much use our auto labels and train the algorithms, and you're still going to get a very, very good performance comparable to many other state-of-the-art algorithms. So this was pretty much it for the presentation. If you have any questions, please go ahead. Yeah, I'm welcome. So also the source code that I didn't want to forgot to mention, you can follow the source code. The code is now there. We just recently released it. But yeah, so if you have any questions, just shoot and ask. I'd be happy to reply. Thank you.
Thank you very much, Sergey. Very, very interesting presentation. I'll ask you everyone